Okay, let's get started. Welcome to the introduction lecture of the nanomanufacturing class. This is being offered for the third time. I'm John Hart. I've taught it all 3 times. It was first offered in fall of 2007, and hopefully it's getting a bit better and a bit more organized each time. We're in this fancy TV studio room because the course is also being offered as a distance learning class for a few of the Interpro Master's programs. So as of now, there are 5 students who are watching the class completely separate from us on video. But the nice benefit of it is we get all this cool technology, plus the lecture videos will be available for you to watch online at any time. That doesn't mean you shouldn't come to lecture, but they're there for you to review, and there'll be a link to them on the C-Tools website for the class. I'm sure we'll find out how to access that later. So the purpose of today's class, the agenda of today's class, is to give an introduction to the course, answer any questions that you might have about what we're going to cover and how the course is going to be run, and also talk a bit about the background and motivation for nanomaterials and nanotechnology. So I'll give some definitions to start. We'll talk about a bit of history, sort of nanotechnology and materials over the ages. We'll go through the course specifications. I'll give some more recent examples of research, applications, and emerging trends in nanotechnology and nanomanufacturing. I'll ask you all to introduce yourselves briefly to the class, and then I'll close with a bit of advice on, I think, how it might be helpful to organize your thoughts and actions as we go through the course. Because one thing is nanotechnology and nanomanufacturing is a very broad and fast-moving topic, and we cover a whole lot in this class, and I think it kind of gets quick, and you get a lot of material. And I think it's important to try to stay on top of things, but recognize that it really is a balance between breadth and depth. And as typical with each lecture, I'm going to post a set of readings on our C-Tools site. And there's no textbook for the class. There really isn't one book that covers all the things we're going to talk about. But we'll often talk about research from literature, and we'll talk about topics that are excerpts from various textbooks, and all that will be provided in PDF format on C-Tools. So for today, there's really no specific material that will end up being on a problem set or on the exam, but the goal of today is to sort of give a perspective of why we're all here. So on the C-Tools site for ME599002, you should all be on there if you're registered for the class, either auditing or taking the course for credit. If you're a visitor or for some other reason you're not there yet, just send me an email and I'll be able to add you to the site, and then you'll get an email that notifies that you're there. I've posted a bunch of PDF files on topics introducing nanotechnology and nanomanufacturing. And you don't have to read all this, and it's probably more than you'll read in detail. But if you do get to read 2 of the articles, I recommend reading Richard Feynman's article from 1959 called "There's Plenty of Room at the Bottom." And this was sort of the perceptual introduction to the field of nanotechnology because he posed some challenges. For example, printing the whole text of a book on the head of a pin. And this is looked back upon as sort of what got people's minds starting to think about the field. And then come almost 50 years later, there's an article I really like by Jim Jimsesky, who's a professor of chemistry at UCLA, called Nanotechnology, the Endgame of Materialism. And this is a mix between sort of practical aspects and more conceptual, perceptual visions of how the fact that maybe in the future we'll be able to control matter at the atomic scale and what impact that could have on science and society. It gets a bit wild in terms of this ultimate control of your mind stuff, but I think it's a nice treatment of both aspects. And this is actually in a journal called Leonardo, which is an art and science journal, and it has that flavor as well. So I highly recommend these 2 articles. And then the rest touch on some more topics of education and economic growth and funding of research, which I think are just, that's not what this class is about, but there are things that I think are nice to think about and be aware of as we decide, what we want to, apply our knowledge toward and why we're all here, giving ourselves to study and learn about science and technology. So there are a bunch of articles on this topic, and these are kinds of things that as more researchers and companies get interested in production and applications of nanotechnology, people in the areas of social science and public policy are starting to do research to look at the effect of nanotechnology on society, and also the effect of government funding in these areas on creating economic growth and creating jobs and getting the right types of graduates from our schools and universities on these topics. And those last articles address those. So by definition, a lot of government organizations have spent a lot of time trying to give a very proper definition of nanotechnology, and the National Science Foundation several years ago said nanotechnology is the ability to understand, control, and manipulate matter at the level of individual atoms and molecules. And, that we need nanotechnology in order to create materials, devices, and systems with fundamentally new properties and functions because of their small structure. So everything around us is made of atoms and molecules, but what nanotechnology really is understanding how to look at and move around the small things and put them together to give new properties, new functionalities that we couldn't achieve before, and also to, in a sense, understand why the things that we have in front of us behave the way they do because of the way the atoms and molecules are organized. And fundamentally, when we study chemistry or physics or materials, it gets down at some level to that fine level. The bulk properties of materials are governed by their atomic organization. And one of the first themes of the class is we're going to think about how the properties of very small nanostructures are different mechanically, electrically, optically, thermally because of the way the atoms are organized and because of their small size. When the size of your structure, the size of your little nanoscale room is on the proximity, on the size of a small number of atoms, or the wavelength of light, or the wave, the distance that electrical wave or a thermal wave, a vibration might travel before it hits another wave, then things get interesting and special. And gee, if we can now change the size of our nanoscale box and our nanostructure, we might see fantastic differences in those properties. And I think that's the first thing that we want to get a hold of as we then think about how to make those structures and how to put them together into large-scale materials. Because certainly we need a lot of those little materials to make even a small piece of something that we can hold in our hands. And for manufacturing, we want to employ these atomic and molecular interactions to develop efficient processes. So to make nanostructures on large scale, you need to understand the small, and you need to understand how to copy the small many times to make things large. And you also need to understand how the small components work together and interact in order to facilitate their assembly. And that gets to a later part of the course where we'll talk about how interactions between surfaces, between structures, are different or special at the nanoscale. And that applies to magnetic interactions, electric interactions, fluidic interactions, and there are specific aspects and nuances that we'll address in each case. And we can ask ourselves what fields nanotechnology includes and impacts, because we all hear that things are getting more interdisciplinary. And there was an interesting study published just a couple months ago where they looked at what fields of nanotechnology or things that express a relationship to nanotechnology are related to. And here you see what is a publication of subject categories in an electronic database, and the size of the bubble determines how many things that say they're related to nanotechnology and say they're related to these other words here exist. And so you can see that a lot of nanotechnology research is related to materials and chemistry, but you see things that you may have thought are far off. Physics, computers, biomedical, medicine, ecology and the environment, and so on. And then another thing they did is they looked at other fields of science that are cited by papers that talk about nanotechnology, talk about impacts or new materials, for example, making small structures for the sake of suggesting they would be useful for something else. And from this you can see that there's a lot of work in materials, but there's work in materials with respect to other applications. So the materials vector here points to applications in the same kind of organization in health and medicine and ecology and the environment and computer science and physics. So clearly, the idea of controlling materials at very small scales and understanding their properties and interactions is an interdisciplinary topic, and there is feedback. There is feedback for understanding how those properties and capabilities could affect those areas in terms of impact and applications. And there's also, interest in people, for example, in medicine and energy and the environment in, asking, well, what could we do if we did this? Or on the flip side, for, the environment and health, another big and important and emerging issue is, what's the fate of small materials and small structures with these special properties and sometimes interesting and extreme reactivities when they go into our water supply and when they go into the bloodstream, and how do we react to that? And in some cases, that creates sort of some caution and some worry, and in some cases, it doesn't at all. And that itself is just another very rich and ongoing research area, and one that we'll pay a bit of attention to in this class. So, if we look at length scales, if we go down from our length scale to the length scale of the nano, each of these pictures steps down some orders of magnitudes from the scale of the universe down to the scale of the atom. And a lot of the structures we'll be talking about in this class, or what we'll refer to as building blocks, are fundamentally quite small. So this is a plastic model of a C60 molecule. It's the same thing as shown in the bottom right picture on this slide, except this doesn't have an atom in the center. And it's called a fullerene, and it consists of 60 carbon atoms arranged in the same arrangement as you would have in a soccer ball. And it's comprised of pentagons and hexagons, and we'll talk a bit more about this later. In contrast, a lot of cellular objects, cells are in the micron range or so, and that means they're 1,000 times or more on average bigger than these well-controlled molecules that we can make today. So you can imagine that how this interacts with a cell or interacts with other molecules is an interesting and perhaps very special problem. And if we look at the length scales in a bit of a different way, this chart shows what we have beneath 1 millimeter, and millimeter scale things are like small insects. It's always nice to consider a size of a human hair as a scale benchmark. So based on how thick or thin your hair is, it's about a few tens of microns in diameter up here on the left. And so that's about 10,000 to 50,000 nanometers. So as you can see, you already need an incredible number of these small structures together if you wanted to, say, make a thread out of them, or make a light bulb out of them that can emit enough light to fill a small space. And we'll wander sort of up and down this axis throughout the semester, but the general trajectory of the course is to start at the small and think about how the atoms are organized, and then work our way toward the top. So we think about how they interact and how we make them and how we put them together, and then hopefully at the end of the semester have a perspective on how we might control the small to realize there's something useful and interesting at the large scale. And that's when we'll get to the project and when you'll propose a topic of your interest as a team based upon the lectures. And certainly, as I alluded to already, you need a lot of atoms to put together to make even a small scale structure. So this graph shows the number of atoms based on just a simple crystal model as a function of a diameter in nanometers. So imagine this is a solid sphere of a crystal of a bulk material, and gee, even something that's even 10 nanometers in diameter already has 1,000 atoms, or 10 to the 3 atoms. So we very rapidly reach large numbers of atoms, but we're still in a range where we see interesting effects of size on properties. And like the range of sizes in which properties change will depend on the material and the structure, and we'll see certainly some examples about that later. But without a doubt, things that are even the size of our hair contain massive numbers of atoms and massive numbers of structures. And one of the very practical and useful and important implications of that is that if you have very small structures packed together, you have a lot of surface, because the area, the ratio of surface area to volume increases as you go down to the nanoscale. Because if you do the math, which we'll do next time, to take the surface area to volume ratio of a sphere, you'll see that it scales with 1 over the radius. So a smaller sphere, a smaller particle like this, can expose a lot more surface. And if you have, say, a powder made of these C60, these buckyball particles, you have a material with a very high surface area, and that can be useful for and interesting for a lot of applications. So certainly nanotechnology, or I shouldn't say nanotechnology is not new, because my point is that nanotechnology is really new, but things being used at the nanoscale are definitely not new. In fact, there are examples as we look back into historical artifacts of actually practical realizations of these size effects on properties in things such as these stained glass windows in a famous cathedral in Milan. If we've gone back now and looked, researchers have gone back and looked at the reason why these different pieces of the glass window have different colors, and it turns out that the folks who were putting these windows together were controlling the size of gold nanoparticles that goes into the glass. And certainly I don't think they realized that that's what they were doing, but it turns out that this size-dependent color relates to how light interacts with a small particle of gold, what's called the surface plasmon resonance. And gee, many hundreds of years ago, there's a practical application or implication of the relationship between a nanoscale size and an interesting and functional property. And in fact, as early as 1889, we started to see things like patent literature on manufacturing of carbon filaments. And this is from a few gentlemen in the UK, and they were using a high-temperature thermal process, one that's very similar to what we'll talk about as used in industry to grow carbon nanotubes today. And in the text of their patent, they remarked on, gee, these small carbon filaments have great strength and flexibility, and they're useful for electrical applications and mechanical applications. Now, they had a bit more information and control over their apparatus than perhaps the folks who built the stained glass window did, but they really didn't realize what they had their hands on, and they couldn't be technologists because they couldn't close the loop. They didn't have the characterization tools and the insights that we have today, and I think we are really at the threshold or on the wave of being able to engineer and manufacture these materials and break through to practical realizations of nanotechnology. And likewise, with the examples on the previous slide, the human race is always curious to look at things and look at things at the smaller scale. And one of the things that motivates and enables our ability to work at the nanoscale is the ability to image smaller and smaller things. So there's a famous guy from the 1600s named Robert Hooke who sketched these beautiful hand drawings based on optical magnification of things like this is the tip, the head of a pin, and he was comparing it to the size of a pollen spore. And this is another drawing, and I think this is a 64th of an inch or something. So he was sketching out the smallest scale that he could sketch out back in the day, and that's as far as we could go back then. But more recently, we can really see what's happening at the true atomic scale. So in 1991, there was a real breakthrough publication that confirmed the structure and existence of carbon nanotubes, which we'll talk a lot about as the semester goes on. And this is used in an instrument called a transmission electron microscope, which we'll discuss when we have a lecture on characterization. And using this instrument, we're actually seeing the individual layers of atoms in cross-section. So this is a top view image. You prepare a sample in a special way, but basically imagine it as sort of like nanoscale spaghetti suspended over holes, and you're using an electron beam to look straight down at these nanotubes, and you see the individual atomic walls of the nanotube by the contrast here and here. So this is a single layer nanotube, a so-called single wall nanotube, and this is a multi-walled nanotube that has multiple layers like so. And the ability to see things like this, although sometimes it's pretty involved and painstaking, is really, really important, because then we can, say, correlate measurements of the electrical conductivity of the structures to their size and their structure and so on. And another sort of milepost on what we may be able to do or what we can do on the small scale with nanotechnology was done by IBM in 1993, where they built a ring of individual iron atoms on a carbon substrate. And this image is taken using a scanning probe microscope, where you basically have a very small probe or like a little fingertip tracing across the surface. And this showed their ability to place atoms individually, which still is very slow and and very difficult, but it's possible using this technology. And then, because of the way the electron waves behave at the nanoscale, they had an atom sitting in here, and then they produced a reflection image of what would appear like another atom over there. But this has to do with what's called the quantum confinement in this ring, and this is an image of this atom which really exists in this position like so. And you're looking at the atomic texture of the substrate here. It looks like something big, like we have a layer of balls on the floor here, but this is really, really as at a fantastically small scale. And some characterization techniques that are used to measure these structures are, for example, electron microscopy, which we'll learn a bit more about later. And that's like light microscopy, which we all know, but instead of using a beam of light, you're using a beam of electrons. And because the wavelength of electrons is smaller, then you can look at smaller and smaller things. And certainly there's still a lot of research in pushing the bounds of electron microscopy, and also now doing things like very fast electron microscopy, so you can take video of very quick processes at the atomic scale. In the past, using an electron microscope, and actually using most that we have, say, in like here at U of M and other universities, it's pretty much you're just taking a picture and you take a slow scan. Well, now what if you want to look at how quickly some event happens, or how fast an electron moves, or how material reacts to a flash of light? That's what people are doing research on with electron microscopy now. And instead of having glass lenses to focus the light, you use magnets to focus electron beams. So in an electron microscope, as we'll see later, you typically have a column like this vertical expression I did for looking down at the carbon nanotube, and you use magnetic lenses to focus and steer the beam of electrons. And if you take a scanning electron microscope picture, the microscope is actually scanning the electron beam across it, rastering back and forth, and doing that at high enough speed so you could see an image as you like it. And then another really pioneering and in fact Nobel Prize winning characterization technique is what's called the atomic force microscope, a variant upon the scanning tunneling microscope that gave the picture of the ring of atoms on the previous slide. And here you're imaging physically. You're taking a very, very sharp tip, what looks like a little stylus or a little finger running across the surface. And the idealization is having a tip that's atomically sharp running across the surface, and you're creating a picture by physically scanning. And there are many modes in which AFM and STM and SPM can be run, whether the tip is in contact or in close proximity. People can do other things like apply voltages or measure temperatures or electron flow between the two surfaces, and they can be done in liquids and so on. And there's a lot of research in this area, for example, for doing things very fast and in, for example, liquid environments for, say, looking at biological processes, looking at how viruses move or how DNA may bind to something. And there is a case where here's a technique that people are trying to apply to, say, directly look at biology, because it can be done in atmospheric pressure, whereas electron microscopy has to be done in vacuum, because electrons don't move, will scatter in an atmosphere, and that also places a restriction on the things that you can look at. So we're not going to talk about characterization a whole lot in this course, but having an appreciation and an overview of how people look at and measure nanoscale structures is important, I feel, to understanding the later synthesis and manufacturing techniques. So we're going to start out trying to build our toolbox with characterization and properties, and then we're going to try to start to put the knowledge together in terms of interactions and assembly. And sometimes now, if we can look at the finest scale, sometimes we find imperfections. And the higher resolution our camera is, or our electron microscope is, the more ability we have to look at how really the atoms are placed and what things may not be in the places we expect. So, as we'll see next time, the ideal structure of a carbon nanotube is like, graphite. In perfect graphite, you have the atoms arranged hexagonally in sheets. Same thing in a nanotube, but because of the way the nanotube grows or deforms, sometimes and practically you have defects. So instead of a hexagon here, we have a heptagon, and next to it we have a pentagon. And this is what's called a stone whale's defect, because it can be imagined by taking one bond and rotating it. So you basically take one atom from one hexagon and give it to the next one. And here in this nanotube, this is probably one of the most advanced electron microscopes in the world. They're able to use their image and use a computer reconstruction to say, gee, well, it looks like we have one of these 5-7 defects in the wall of the structure, and instead of this perfect hexagonal lattice, we have an arrangement like that. And this is very, very difficult to do, but the ability to do this and the ability to, say, take a measurement of the electrical conductivity of this structure or some other properties lets us now start to close the loop and engineer and understand how truly the smallest atomic transformations affect the properties of the materials we work with. And in that regard, I think we are really trying and really starting to close that loop. And there are more and more demonstrations of dynamic, functional hierarchical system level things using nanoscale components. We're still very far and may never reach the idea of having these nano assemblers and nano machines that carry us down the street, or will build a table upon command. But for example, people have demonstrated the motion of molecules in an example like a macro scale rack and pinion. So here you see a scanning probe image taken using a scanning tunneling microscope with a sharp tip of an individual molecule that looks like this wheel here resting on a terraced substrate. And if you look at this paper from 2007, you'll see that they did a statistical analysis of how the molecule steps across the substrate and what the effect of the interaction between like this atom and the next atom is on the probability of it rotating sort of on this corrugation. And the thing is that because these structures are so small, gravity is really irrelevant here. So what dominates is the atomic attraction due to the interaction of the electrons from one atom to the next, and that's a topic we'll talk about later. So things kind of are gluey and sticky at that scale, rather than imagining something, a big wheel rolling down the stairs. But in terms of the physical contact, it turns out it's analogous. And then another area is using inspiration from biology to assemble structures. And an area that's been around for about 20 years but now is really growing is the ability to program biological molecules such as DNA to assemble into complex and synthetic things. So this technology has been called DNA origami for several years, and the basic idea, which we'll talk about quite late in the semester, is that because you can say sequence a DNA strand the way you want, you can sequence it so you can program the interactions, the chemical interactions between one strand and the next. And by combinations of programming the strand sequence and controlling the length and understanding how different codes bind together, researchers are starting to make quite interesting and fascinatingly complex things, like say 40 nanometer size geometric structures, icosahedrons, made from twisted backbones of DNA. And this is actually starting to be used to place nanostructures on the surface, because if you can engineer the interaction between, say, one of these little triangles and something like a fullerene or a gold nanoparticle, and if you can then very precisely tile these triangles together and then take, say, a sheet of tiles and put them on a silicon wafer, then you can integrate something from self-assembly, from kind of the bottom-up interactions that I'll define in a moment, and lithography, or the top-down processing that determines how pretty much all of our computer processes and electronic devices are made today. So we're starting to see these kinds of inspiration and use of the bottom-up manufacturing of nanoscience and nanotechnology in commercial applications. And we still do have a long way to go and a lot to understand. And this slide does compare between those top-down and bottom-up methods. And the terms top-down and bottom-up are used in a lot of fields. But in the case of manufacturing, a top-down process is a classic one of taking a piece of material and removing the things you don't want, or taking or making your final shape by subtraction. So this shows a milling machine, classic example from mechanical engineering. And if I have a block of aluminum and I want to make holes in it, I might just pop it in the mill and drill those holes out. While a similar type of technology is used to create electronic circuits and microprocessors, not by taking bulk metal, but by taking silicon wafers and using photolithography to etch small features and then deposit films and pattern films and etch them, and lo and behold, you subtract and then you build up circuits and processors and things that interact. And then the opposite vision of bottom-up manufacturing is that we start with, say, a substrate, such as this table, and we can just supply the things that we want, and they find their places and they self-assemble. So here's an example of a self-assembly of a monolayer, perhaps one of the simplest examples of bottom-up manufacturing or bottom-up assembly. But here, because these molecules have favorable interactions with the substrate, if we can engineer the atoms on the end so they like this blue substrate here, and if we know that they can favorably pack like this, then over time and correct control of the conditions, you can effectively grow a very uniform single molecule layer called a self-assembled monolayer. And you can imagine now integrating processes where we, say, start out with a substrate and cut out little holes and coat those holes where we want these molecules to go, and then dip it in the solution where these layers will self-assemble, might let us integrate some inspiration from top-down manufacturing and bottom-up manufacturing. And we'll try to keep this comparison alive throughout the semester, but this kind of stuff is what we're really going to focus on, hoping that it's complementary to knowledge that's provided in other classes and knowledge that you might have from other research or coursework. And our perspective of this bottom-up manufacturing is really going to be built around this idea of having building blocks. And I'll use the term building blocks for nanomanufacturing as referring to different classes of small structures where we can start and understand what their properties are like, and then start and look at their interactions, then how to make them and how to put them together. So by definition, we'll say that we'll look at nanoclusters, which have very small numbers of atoms, tens or hundreds of atoms, or so-called magic numbers of atoms, like this C60 molecule that has exactly 60 atoms because the 60 atoms fit together in a very precise way. You don't find C61, you find C60, and you find like C120 and other magic numbers that have structural stability because of the way the carbon bonds want to go together. And then we'll talk about nanoparticles. And this is just more kind of a nomenclature, how I'm suggesting we write our own dictionary, but one that I think is pretty accepted out there. And nanoparticles are things that are generally round like these nanoclusters, but have a significantly larger number of atoms, and therefore are in the size range of many to, say, about 100 nanometers. And in the nomenclature of the field, these structures in the top row would be what people often call zero-dimensional structures, because they're essentially three-dimensional, but they're really, really small, so it's like a confined box for the stuff that's going to happen mechanically, electrically, thermally, and optically among the energy carriers in this small space. And then we'll talk about another set of building blocks, nanowires and nanotubes, where it's like taking one of these and extruding it along a distance. And actually that in some ways is how some of these are made. Sometimes you use one of these as the seed to grow a long structure like so. And in this case, we have what are referred to as one-dimensional structures, because you can have these nanoscale pipes or wires or tubes, and you have very interesting transport properties along their axis. So this can be like a very, very high-velocity tunnel for electrons, or it can be a very, very strong wire, or a very interesting sensor, because it has that very high surface area relative to its volume. And we'll see a bunch of examples of all of those. And in the nomenclature down here, the distinction between a nanowire and a nanotube is just that one is filled and one is hollow. And there are some materials in which you can make both nanotubes and nanowires, and there are other materials that, because of their crystal structure, you typically make nanowires, and others that you typically make nanotubes. For example, graphitic carbon wants to be sheets, so you're more likely to make a tube of carbon rather than a solid wire of carbon. Silicon wants to be a three-dimensional crystal, so you're more likely to make a silicon nanowire rather than a silicon nanotube. Or you might have to use some more interesting strategies to kind of like maybe cut out the center of the silicon nanowire if you wanted to make a tube, and we'll see some cases of that as we move forward. And this chart sort of expresses the top-down versus bottom-up idea of manufacturing, in that on the left axis it plots complexity, and on the horizontal axis it plots size of the structures. And what we're looking at here is the arrow that's going from the bottom left to the top right, and the arrow that's going from the bottom right to the top left. And the idea of the top-down process, what gave us the first transistor decades ago, at the scale of about 1 millimeter, is that we're continuously reducing the size of things that we can kind of cut apart and build up ourselves. So we went from millimeter scale transistors now to about 1 or to 0.1 nanometer transistors. And they're making lines that are tens of nanometers wide using technology that enables lithography much smaller than the wavelength of light, and that's in all our cell phones today, using this kind of top-down process. That has a lot of nanotechnology and nanomaterials in it, because the ability to make these, say, wires smaller and smaller by cutting puts things into the size range where their properties are a bit different, as we'll talk about later. But it is distinct from the bottom-up process, which really is one of self-organization. And you could argue that we are all, self-assembled objects of bio-nanotechnology, that, something that's living and breathing and moving is perhaps the most complex machine that we know. And we're learning even more about how our own bodies work and react to our environment and how disease grows and spreads. And that, at some level, has to do with the atomic and molecular interactions of all the things that make us go, and how the rules of DNA and transcription and molecular interactions and responses to chemical and electrical signals create these hierarchical behaviors. So, some people's dream or fear or both is that one day we'll be able to engineer, synthetic organisms, but, it all has to do with the interactions among the things at the smallest scale. And we'll just start to talk a bit about that in this class. And as this understanding develops, we hope to get more and more complexity growing in the future. And this slide is from Mikhail Rocco, who has been at NSF for some time and was one of the pioneers of the National Nanotechnology Initiative. That's a big government organization that directs nanotechnology research through a bunch of agencies such as the NSF. And he sort of laid out a roadmap. Times are sort of relative here, but how, as we learn how to understand and put together and assemble these objects at greater and greater levels of hierarchy and sort of understand behaviors among them, how we'll be able to make more active systems. So we'll see some examples in a few slides of how there are already a lot of consumer products that comprise nanostructured materials. Like there are a lot of carbon nanotubes likely in our cell phone batteries, and they have a specific and defined and important function, but it's far from having, say, a circuit that can change its connectivity based on some stimulus, or some molecular surgery thing that can go into our bodies and can, say, grab off a piece of tissue in a diseased area by recognizing something, or something that will move in response to light and transport a certain material. And these specific things are not so important as than just the idea that we're moving from passive nanostructure technology, coating and additives, to active technology based on understanding how the materials work together and how they might sense and respond to their environment. And the more we understand about that, the more we understand about how to employ those things in manufacturing processes. And this slide is from a company, Lockheed Martin, rather than sort of a visionary about research. And it's interesting to me to see how the long-term vision of someone who wants to forecast technology and research sort of collides yet overlaps with the vision of a company, Lockheed Martin, that makes a lot of advanced materials for energy applications and military applications, and thinking about all the things that are really needed to make products. And now they talk about economics and standards and measurement and quality control and modeling and simulation and scale up and characterization and all the kind of traditional manufacturing words that we might think of if we're making cars or making solar cells or making computers. And all those ideas are also essential to scale up of nanotechnology, because you need to make things precisely and predictably and understand their performance over their life cycle. And as more examples of true nanotechnology and nanomaterials get more into the marketplace and more into production, then there'll be more involvement of those fields with specific application to nanostructures and nanotech. And that is why I really choose to call this class nanomanufacturing, not because there's a lot of existing, out there large-scale machine manufacturing that we're going to take, but I really feel that it's an important inspiration for, thinking about the topics we're going to talk in this class. And this means that there's a lot of need and there's a lot of opportunity. And I think that's why I'm here, and that's why I hope we're all here to talk about and learn about this subject together. Again, there are a lot of studies that talk about how much research and how much education that's going to happen. And Rocco a few years ago said that in 10 to 15 years, the world will need about 2 million nanotechnology workers. And you might ask, well, what is a nanotechnology worker? Well, maybe it means that someone who is just trained in the processes and characterization techniques that encompass, all the kind of connections that we saw in that big diagram at the beginning of the lecture. And this means that people can also forecast the economic impact of nanotechnology over the next number of years. And numbers always vary, but suffice to say that because people are relating all these areas and doing work with different applications, there'll be a significant economic impact because of these new materials and devices on materials, electronics, and so on. And this is going to be important to our economy in the future. And that also gets standards organizations involved because, like the Lockheed Martin previous slide, we want to understand how to compare materials from different suppliers and how to use them in standard manufacturing processes. So there are many international standards organizations developing standards for working with nanotechnology. In fact, there's a current effort on developing a standard for incorporating nanotubes and nanowires in microelectronics fabrication. So for example, if we had that ability to hook DNA to carbon nanotubes and then stick them across, to make wires where we wanted to, how would we analyze the purity of that material and how would we actually bring it into a standardized process and therefore be able to call up a company that makes circuits and has a clean room and say, I want nanotubes across this size gap and so on. That's something that we all might do if we wanted to design a circuit today, but we wouldn't be able to use these new materials unless that standard existed. And those thoughts are beginning to happen, and we'll also touch on a bit of that. All right. So are there any questions at this point? Feel free at any time to raise your hand and ask a question. And that's always the case in any of the lectures we'll have. So now we'll spend a few minutes talking about the objectives of the class and the structure of the class. And then I'll talk a bit more about some specific examples, and then we'll finish up. So I think that our mission in this class, Nanomanufacturing, has about 5 points. And the first topic is to understand the fundamental properties of nanostructures, the building blocks we reviewed already, nanoparticles, nanotubes, nanowires, clusters, and so on. And we'll talk about that for a couple weeks. If you want to guide yourselves, you can flip open your syllabus to the third page, which shows the lecture schedule. And so the first bullet up there is topic number 1, and we'll be on topic number 1 for the first 6 lectures, excluding this lecture. And then our second part of our mission is to understand how nanostructures interact with one another and their surroundings. So that's when we'll get to understanding intermolecular and surface forces. For example, what caused that gear to roll over that atomic staircase, but in a different way than a big gear might roll down a human-sized staircase. And there'll be surface energy issues and double layer and slip flows and plasmon resonance and all these kind of interactions that we'll learn about. And then in the third topic, we'll talk about how to make and assemble nanostructures. And I think you need to know a bit about the properties of the structures and how they interact to learn how they are made and how they're put together. And we'll talk specifically about examples of how to control their size and structure and placement. Because it's actually, there are a lot of materials that if you take them through a thermal process under the right conditions, what actually that patent from 1889 making carbon filaments was doing, you're going to get some nanostructured materials. Certainly, you'll get a lot of little particles, and in fact, you might get some carbon nanotubes. In fact, people have seen that there is a very, very, very small percentage of carbon nanotubes in diesel exhaust. But our goal here is to really understand how to make a lot of them and make them predictably with the right size and the right scale. So now we can say, well, I know that I want a silicon nanowire of 2 nanometers diameter because it has property A that's useful for my solar cell. Well, how am I going to make it so I have 2 plus or minus 0.2 nanometers diameter and have that really, really good process control? That's difficult, and there's still a lot of work to be done in those kinds of areas, but we're starting to see and can in fact relate some concepts from basic chemical kinetics and nucleation and growth to the processes that make these structures. And those are the kind of analytical tools and theory that we're going to bring into the topics, those sorts of topics. And we'll understand how to make and assemble structures, and then we'll understand how the properties of nanostructures scale based on their assembly and interactions. And so I guess the third and fourth bullets here are really topics 3 and 4 on the syllabus, although topic 3 here spreads into topic 4 on the syllabus. And then we're going to focus on kind of large-scale processes, integration of top-down and bottom-up methods, the idea that I mentioned with regard to, say, integrating some biological components or some self-assembled components on substrates. And then our goal is to use our knowledge to put it together to design new devices, materials, and processes. And that gets us to the project where I'll want you to propose what you feel is a really, a new idea. It can be a wild idea, encourage, creativity and wildness, but one that can take the principles that we discussed in the class and connect it to a topic of your interest. And so the outline of the course follows that mission statement very much. And the assignments for the course, you can look at the grade percentage distribution on page 2 of the syllabus, comprise 4 problem sets. It's 4 problem sets. I think this is a typo on this slide. 1 exam, and a literature review presentation, and a project. And I'm actually not sure what the literature review presentation is going to mean. I'll talk about in the next couple lectures, and maybe I'll ask your opinion whether you would rather do a literature review presentation, which means take a couple of journal papers on a particular application or topic related to a past lecture and give a short presentation about that, or whether it be better to do some kind of report or wiki type assignment on a specific lecture topic or an extension of a lecture topic. And that also depends on how many people remain registered in the course, because I don't want to take too much lecture time for the literature review presentation. So you don't need to worry about that until we talk about it more in the lecture. And also note that there's 10% for attendance and class participation. I'm not going to be taking attendance every day, but given even the present size of the lecture, I want you to ask questions and interact and get to know who you are. And this will be a very a digital or binary thing at the end of the semester, something like a 10-5-0. So if you're here and you've been involved, you can get 10%. But if you don't show up or you don't say anything, I don't want to penalize you too much. But I want to encourage you to interact and ask questions and get to know others in the course, because I think that collaboration is also very important, a part about learning so many new topics in a short time and working together on assignments and synthesizing knowledge from different fields. Okay, question?
There's a lot of pictures of these nice perfect structures,
yeah.
But since in microscopic processes, all processes, you want to maximize entropy,
yeah,
and you get more entropy if there's defects.
Mm-hmm.
How robust are these
It depends.
things?
Certainly, as things get bigger, you're going to have more flaws. The statistical distributions of defects and the effects of atomic defects on properties of nanotubes and nanowires are really not fully understood. Like, you can take an example. On the next slide, I'm going to show a picture of a TM image of a quantum dot where it looks like the atoms are fairly well organized. You always, I guess, have some distribution of probability as something gets put together. But if one configuration is relatively more energetically favorable, then you're less likely, say, to form a defect. Say crystallization of a certain of a certain crystal, there's always an activation energy for forming a defect or, say, forming a dislocation. And if that dislocation then forms, then maybe you are off in an undesired direction, unless you can, say, reset the process to bring it back to its other state. So, kind of a vague answer, but I don't think there's a specific one, other than that, I guess the goal is to make the structures of the right level of flaws that you want. In some cases, flawed structures are actually useful. If you wanted to, say, create a material with very low thermal conductivity, you might want to be able to break it up into small pieces, so you block the vibration waves which govern the transport of heat across the structure. In other cases, you might want to make the crystal as perfect as possible, and in some regards, both of those are challenges that are yet to be met. But we're continually evolving our knowledge on how to do that, and I hope that as we go on, we'll get a better and more specific answer to that question. That's a very important one. Okay, so this slide just talks about some applications of nanotechnology and nanomaterials that are here already or coming. And one of the, I would say, most famous photos of nanostructures ever is this picture taken by Felice Frankel from Munji Buendi's research at MIT. He was one of the pioneers in developing what are called quantum dots or semiconductor nanoparticles. And as we'll learn within a couple weeks, the relationship between the size of these semiconductor nanoparticles and how their structure reacts to light, their optical properties, can change their color. Basically, if you hit one of these particles with light, you excite an electron, and then the electron drops back down to its ground state, and it drops down across the band gap of the material. And the size of the particle changes the band gap, which changes the energy that is emitted as the electron drops down to the normal state, and that changes the energy of the photon that's emitted. And the energy of a photon determines the color that we see. And so here in each vial, you have different colors, different sizes of nanoparticles, and therefore you see that. Because they interact with light in a very specific way, there's a lot of work on putting these and mixtures thereof in solar cells and detectors and light emitters to interact with light in different ways. And that's a very ongoing field also for molecular imaging. Say to hook it to a biomolecule and be able to attach it to a tissue area of concern in your body and see a very bright fluorescent signal is a very useful and practical thing. There's also work on, for example, using carbon nanotubes to make memory. And here we're looking at not an optical application, but a mechanical application. And there's a much more practical twist on this that we'll see in a little while. But the concept here that came out of Charles Lieber's lab at Harvard in 2000 was an idea, well, how do we make the densest memory possible? And how do we store as much information without using power? And their idea was to take individual carbon nanotubes, which you can imagine as very stiff, small rods, and create a lattice of them, or a lattice where one direction runs at one level and the other direction runs at another level, and there's a little bit of a gap between them. So just like a bridge over a road, but what they theorized would happen is that if you applied a voltage between the bridge and the road, you could then, because of the electrostatic attraction due to the opposite charge, pull the top nanotube down onto the bottom one. And because of the strength of the intermolecular interatomic forces, so-called van der Waals forces at that stage, if you turn the voltage off, they would stick. And then you could store that as a bit of information, a 1 or a 0, relative to the other state. And gee, if you could make this lattice very, very dense, and you could precisely control that gap, then you could store a high density of information. And also that now if you reverse the potential or you apply the same potential to both, then the idea is that they would pop back open, and you would be able to get rid of your data and store new data based on what you wanted to do. And in fact, at that time, in concert with this paper, they demonstrated it worked for 1 by 1 or 2 by 2 and started a company called Nantero, which is still working on this. There are also a lot of applications in drug delivery and bioimaging. Just imagine all types of nanostructures and how they could interact with biological structures in your body, or how you might be able to make, say, carbon nanotubes with DNA hooked to the surface or other molecules hooked to the surface, and use them for imaging and treatment and delivering drugs and so on. And this is a big and very rich area of which there are already some treatments and emulsions and things that nanoscale things that are used to introduce things that you would buy from the drugstore into our bodies for particular applications. Another example that is on the market today is use of nanostructured materials in battery electrodes. And this company came out of a lab at MIT, and it's probably one of the examples of the fastest moving nanotechnology companies to date. And what they realized is that if you make the electrode of a battery, so a battery electrode is designed to be able to store electrochemical energy, for example, to shove lithium into a solid material, and then that's your stored charge, and then when you want to power something like a power tool, then you let that lithium out of your electrode and a current is generated because of the electron transfer that occurs when the lithium comes out of the material. And a big problem in batteries is that if you imagine wanting to shove lithium into another material, if you put a lot of lithium in it, it's very excursive on that material. The material gets all stuffed up like it's eaten a big meal, and if it eats a lot of meals that are too big, it cracks up and degrades quickly. And that's what, for example, makes batteries go bad or makes batteries lose their ability to hold charge over their lifetime. And what they discovered is that if you can figure out how to make the particles of the electrode very small in the right organization, you can store lithium very well and very efficiently and get it in and out very fast without a lot of this long-term degradation. And their first product, connecting that with sort of the consumer marketplace, was to make cordless power tools, to hook up with Black & Decker, but make cordless power tools that could not previously be cordless because they needed so much power. So things like construction drills that can drill through brick walls and things like that. But it very much relied on their study of the nanoscale properties of their electrode material. And in fact, a lot of carbon nanotubes are used in batteries and have been used in batteries for a long time, not because they can do specifically this, not because they store lithium, but because mixing the traditional battery electrode powders with nanotubes can kind of distribute the stress as all that lithium gets shoved into the electrode material. And we'll talk about that a bit more as the lectures go on. And another commercial application to date is using nanocomposite materials, in fact mixing small amounts of nanostructured clays and carbon nanotubes and graphite in some sports equipment. So there are many companies that have tennis rackets containing nanostructures and nanocomposites, or carbon fiber elements for bicycles or baseball bats. And here is a case where there is a legitimate improvement. For example, baseball bats, aluminum baseball bats with a bit of carbon nanotubes added to the material are better at damping vibration when the bat hits a ball. That is a functional and small improvement, which honestly, wrapped on with the marketing of it containing nanotechnology, has made a very big improvement. Also, the incorporation of small amounts of carbon nanotubes in composites for golf shafts has made them lighter and more, stiffer, yet providing a better feel, and making a slightly better golf shaft in combination with it being, this quote, cool nanotechnology has been an extremely successful product for the shaft company Aldila and the company Zyvex that developed the chemistry to disperse the nanotubes and to mix them with polymers to get that improvement in properties. That said, the types of improvements that are being seen in these composites with the current way that nanotubes are made and are mixed with the polymer is, say, 2 orders of magnitude below what we might be able to have if you could grow continuous long nanotubes with the true strength and stiffness of the individual structures. And that remains one of the big challenges of controlling the manufacturing processes a lot better. And this slide gets into a bit more detail of the application of using these quantum dots for optical and sensing and emitting applications. And for example, here we see a transmission electron microscope image of the cadmium selenide quantum dots here with different crystal structures. And you can see how the organization of the atoms is a bit different, and how, it does seem that there is a pretty good level of order in this structure. But maybe if we had a way of slicing and looking at each plane of atoms, we would at some point see an imperfection. And well, the surface is certainly not perfect, and probably the precise structuring of the surface has a practical impact upon the properties. And for these semiconductor particles, as for metal particles, albeit for a different mechanism, which we'll understand later, the wavelength of light that the particle emits, or that we see, depends on the size of the particles. And so you can go, if you can control the synthesis to tune the size and have one size within a certain tolerance range, you can then create a bit of a blue vial versus a red vial. But if you can't control your process to get enough size control, say in the blue size, and you have a mixture, then you're not going to have blue or red. You're going to have you're going to end up with just one color. And so implied in the ability to do this is the ability to control the size in the manufacturing process, and or to separate them after manufacturing to get this kind of monodispersity. And this is just a diagram of how the particle reacts in response to light. For example, if I hit one of these particles with light, it'll excite an electron to conduction band, and then the electron will decay non-radiatively down to the lowermost conduction band, and then it will drop across the band gap to its native state. And based on this energy, this band gap energy, which depends on the size, we'll see a photon emitted with the energy corresponding to this color. And changing the size changes this distance here. And certainly, in order to excite the electron, I need to have a light excitation, have enough energy in the light to get it across this gap. And this basic process will be a topic of a lecture later on. And then a few more details about the carbon nanotube memory. The idea is that pulling that top nanotube down to the bottom nanotube is a reversible electromechanical junction, and this relies upon the contact properties of the two structures. And the idea is that if you pull the structure down, it ends up stuck in an overall energy minimum because of the interaction, the attraction between the two nanotubes as you bring them close. And then when you take the voltage off, when you take your force off, they will stick, and then you can reverse it like so. And although it's very difficult to make these individual nanotube lattices, what the company has ended up doing is, instead of, you can't pattern individual tubes so precisely, they ended up creating sort of nanotube fabrics, and then using lithography, using top-down processing to cut them into very narrow ribbons, and then create little strips of nanotubes that each contain many of them but behave in the same way. And it's honestly not as dense, and it's not as inexpensive as like flash memory that we have, but for some applications that, say, for things that go in space and take a lot of radiation or need to operate in very extreme environments, high temperatures or low temperatures, because of the properties of carbon nanotubes, they've been an attractive product for those areas. So this Nantero is still around, but they've ended up, I think, feeding a lot of space and defense applications rather than consumer applications. But their process is integrated in a bunch of clean rooms, and they're also one of the companies that's driving the development of a lot of these standards for incorporating nanomaterials in semiconductor manufacturing, because they are trying to make products that do this. And there's also a company that Nantero has worked with called Brewer Science that sells commercial dispersions of nanotubes that can be spin-coated like a photoresist. And it's quite an expensive thing, but folks who want to, say, try to do photolithography on a nanotube layer can buy this well-engineered and characterized dispersion, this kind of nanotube ink, and take it into the clean room, like you could take it into LNF here, and use it kind of like a photoresist and process it as a layer. And that's something that has come out of their many years of development toward this eventual concept. So even though their first concept couldn't be made, they've pushed forward and ended up with something that is a compromise between their science dream and the practicality of the specific technology that they're making. And to talk a bit more about this idea of property scaling, I mentioned how things like sports equipment we have made out of carbon nanotubes today are far from the individual properties of these nanostructures. So one of the big interests in nanotubes has been that they're lightweight and strong, and because of carbon-carbon bonds being among the strongest in nature, if you take the strength and normalize it by the density, and you take the Young's modulus and normalize it by density and do one of these so-called Ashby charts, you'll find that like individual carbon nanotubes are way above pretty much everything else. I mean, certainly way above plastics and so on, and way above metals, but way up in their own category. And so that's created some dream that, gee, if we could make a fiber out of perfect nanotubes, we could make the best cable ever that would conduct electricity and heat and also hold a 747 with a single 5mm diameter cable. However, if you look at the current progress of people who are trying to take individual nanotubes and make them into yarns and fibers, you see that we're actually getting better than metals, but we're still nowhere where the individual nanotubes need to be. And this is because of defects in the individual nanotubes that compromise their strength, and also is because of controlling the interactions among the structures to get them into truly kind of this tightly packed configuration that we want. And so going from here to here is where we need to be, as well as to bring the cost and feasibility of processes to make things like nanotube fibers into action. And but there are companies that also, for example, are making sheets out of carbon nanotubes, and we'll learn about this process later, but I can pass this around. This is a sheet of single-wall nanotubes made by essentially spraying the resulting nanotubes from a furnace and processing it so it gives some alignment to it. And I like to think of organization of nanostructures as kind of a map between the order and the quantity we need. And for things like carbon nanotubes and other structures, the eventual application that we're going to use them in has an influence on the manufacturing process that we need to use. For example, if we needed to make a transistor with an individual carbon nanotube as our wire, we would need just one structure, a very small number, a few of them, with a pretty high degree of order. And as we'll discuss later, we might want some specific control over the electrical conductivity of that structure. On the other hand, if we wanted to, say, disperse nanotubes in a plastic to make it electrically conductive, mix it in a battery electrode material, such as done today, we need a much larger number, but we don't need such high order because we can just have this uniform dispersion and mixing going on. And depending on how we want to organize the materials and what the requirements are, this has an effect on the manufacturing process we use. So because Nantero couldn't do this with a lattice, they ended up doing this, creating a network of nanotubes, kind of like a thin layer of spaghetti. And this is really challenging in terms of purification and making that layer uniform and repeatable, but it was somewhat easier than getting the individual nanotubes placed. And there are also different configurations we'll discuss. For example, vertically aligned structures. So if you're growing a bunch of nanowires or nanotubes in a substrate in close proximity, at the start of the process they can touch each other, and because of these interactions that make them stick, they might self-organize and form kind of what's called a carpet or a forest. And then once they're in that vertical configuration, if you keep feeding the chemical goods you need to grow them and the growth sites remain happy, you can keep producing this mat to get films that are ending, even millimeters long. And here are examples of vertically aligned forests of nanotubes that are growing up on a silicon substrate. So if you take the SEM and you zoom in at the micron scale, you'll see what look like a whole bunch of vines or trees. This representing on each square centimeter of this substrate, there are about 50 billion vertical nanotubes in parallel. So please don't open the package or touch it, but take as close of a look as you want. And I feel like this directly relates to the applications we can realize. So in concert with the previous slide, we're going from things like individual structure devices to bulk materials. And in the context of carbon nanotubes, this relates to the things that we can realize practically. So because we have more technology to deal with this so-called bulk manufacturing and dispersion process, we can make batteries and plastics that are conductive. As we learn how to make nanotubes longer and more ordered, we can move into applications of things like these forests that you're going to see in a moment for thermal interfaces, for filtration membranes, for composites. And then as we develop higher precision in placement and in control of the diameter and hence the electrical properties of tubes, we can move over into this space. And this is, in some ways, I feel analogous to Rocco's idea of making more productive and complex organizations as we understand how to make the structures and how to put them in the places that we need. And in addition to carbon nanotubes, there are a lot of examples of bulk nanomaterials produced today by understanding how to make small structures in bulk, but maybe really not the true atomic level of control. But there are a lot of silicon nanoparticles and titanium nanoparticles used in cosmetics and delta fillings and sunscreens and so on. In fact, there was an MRS Bulletin issue in 2007 on the material science and nanostructures of cosmetics. And there are companies that produce, indeed, very large quantities of carbon black nanoparticles. They go into tires and also carbon nanotubes that go into batteries. In fact, there were large companies in Japan producing multi-walled carbon nanotubes several years before the, quote, official discovery of nanotubes by Ajima, when that beautiful electron microscope image showed the structure of a single-wall nanotube. So in all regards, the field is not new, but doing these kind of special things is really on the forefront. And if we look forward to the kind of things we're going to touch on in the class, we're going to talk about things, for example, that govern the mechanical properties of structures like nanotubes. How these defects, in fact, the 5-7 defects that were mentioned before, actually cause glide of a dislocation and elongation of a carbon nanotube as you pull it along. And we'll talk about how, for example, nanowires are made by this process of precipitation, where a nanoparticle, in fact, is a template for growing a nanowire. And you start out, in case of making a silicon nanowire, you can start out with a gold nanoparticle, like a little piece of gold dust, floating in a furnace, and you fill that furnace with silane, a silicon-containing gas, and you form a liquid mixture of gold and silicon. And when that becomes supersaturated, much like you might grow a macroscopic crystal, you end up spitting out a silicon nanowire out the bottom side of this gold particle. And if you keep the reaction going and understand the limiting mechanisms, can make this happen for a long time, and you can grow the nanowires or nanotubes really, really long. But as you can imagine, if this is a high temperature environment, the gold might be evaporating or might be diffusing along this wire, and maybe that would let you, say, taper the wire to a point. Or maybe it would be bad if it tapers or has some funky surface structure, and those aspects of our control are important for doing all that we're going to do. And then we'll talk about interactions and assembly. This is an example of a nanocomposite made by hierarchically layering different structures, polymers and clays, sort of nanosheets. And these are examples of self-assembly of micro and nanoparticles. So imagine, like this room filled with ping pong balls, but where each ping pong ball is a nanoparticle, and gee, because of the strength of attraction due to the nanoscale, maybe we can tile the room very precisely in 3 dimensions if we just kind of like take a hose and shoot a liquid solution in it and then let the liquid dry so the capillary forces stack up all the particles precisely. And that actually is a process that's widely used to induce self-assembly of these nanostructures. And really a lot of people forecast that it will maybe eventually end up in an end game of being able to control all levels of matter and sort of, comparisons between material and consciousness and control of our brains and so on. And, I think we're pretty far away, but to me it's also one of the interesting things to read the literature about nanotechnology and read how the public react to it. So this is the cover page of the second article I think you should read. And Jimczewski really talks about this idea, of an endgame of materialism, but also a lot of impacts to economy and society. And people have fun with nanotechnology too. Dilbert writes cartoons about having a more interesting and attractive job that has to sound good. So why don't I invent a nanotechnology stem cell for fighting terrorists? And even I saw on TV a couple weeks ago this car for $29.95, which calls itself the Zero Gravity Nano because it can drive up and down the wall. And they have a cool video and shows it zipping around. And I'm guessing it has just like a high surface area adhesive, kind of like a super Post-it note, and lets you stick it on hopefully a fairly smooth wall, and it can drive up and down and around. And certainly people are starting to take advantage of the name of nanotechnology as well. And it also creates the hype of things like Michael Crichton's book, where people imagine these swarms filling the room. But we really are far away from that, but it also means that people's eyes and ears are on the technology that we produce. And so just getting to the end here to talk about sort of a few of these topics of perception and awareness that I think are important for new technology. There is all this research that analyze the impact of nanotechnology in other fields on gee, how do people react to new technologies? And so this study said in 2008, over 80% of Americans reported knowing just a little or nothing at all about nanotechnology. Well, probably heard of iPod Nano, but haven't heard about really what nanotechnology is. And it's interesting if you were to look into this paper to see that people's familiarity with other technologies, like how often they use the internet, or whether they're afraid or don't mind genetically modified foods, has an effect on their perception and their familiarity with nanotechnology, like how risky they think it is, if they believe in the Michael Crichton fear of nanotechnology taking over and swarming us all, or if they believe in the promise of it being able to cure all of our diseases, both of which may never happen, but people's perception affects how they react to the things we produce. And this also relates to socioeconomic background and countries and so on. So there's a lot of interesting research in this area, which I think becomes a nice side topic to get us started in this course. And sort of the last slide I have before we get to some advice for the semester is what George Whitesides from Harvard says is sort of the way that all technology trends happen, is that when people start talking about what might be possible, expectations go up, and then there's a lot of exaggeration, and people get really excited, but then things don't really work or they aren't scalable, and then there's a lot of disappointment, and things kind of crash. And then over time, those who stay keep working hard and keep plugging away what really matters, and then over a longer time scale, we get more and more realization. So I think this chart applies well to the field of nanoscience and nanotechnology, and maybe it's hard to apply it to the field uniformly because there's so many things, but I think every subtopic in it could be plotted in one regard this way or another. I think we are like generally in here, where in some areas where we're still feeling disappointment, in other areas we're starting to see the realization, and probably in some areas we're also just starting to have the exaggeration. But there's a lot of motivation, and I think that if you look at the literature in terms of the things people are doing with nanostructured materials and in looking at energy applications and biological applications, the technology is really real, and it's an exciting time to be studying this topic. So in the interest of time, I was going to do introductions today, but I think I'll ask you all to introduce yourself maybe at the beginning of the next class. So I first want to make sure, are there any questions? Okay, so I just have a few slides that I kind of go through at the beginning of any class that I teach, and I think they're useful for this class because the class covers a lot of topics. So my advisor in grad school, who worked on machine design largely, really liked the chart shown here, which he calls the cost-performance curve. And my point here is that we're going to talk about a lot of topics in this class, and I think I talk fast. I get a bit excited about lecture, and things move quickly, and you don't need to be totally on top of everything that we talk about. And a lot of the material may be new. And I don't mean this as making it sound like I think you don't have background in this area, but we do talk about a lot of topics. And I know from past semesters, students sometimes feel a bit scattered on all the things that come out. And that in some point in the class, it may seem like each lecture is an entirely separate topic, and there'll be a lot of reading and so on. So the overall goal is to feel like you have an understanding and appreciation for the things that we're talking about, rather than to grasp all the details of the theory and the calculations that underpin it. I hope that at the end of the class, you're in a position to feel like you've acquired some knowledge that you can apply to a more specific area of interest, as well as a general overview of the field. And I feel like the way to do that is to go through all these topics and to build up from the small to the large. And so back to this chart, this is sort of just showing the idea that if you look at different processes, in this case, Alex was looking at different types of mechanical systems for achieving motion. You can say build something, and you can achieve at some point you can achieve more and more and more performance with a certain and not so increasing level of cost. So maybe it's kind of like studying in a class or working on a homework assignment. But then there'll be some point where you hit the knee, and it takes a lot more time to do to get a lot more performance out of it, and then you hit sort of this cost-performance curve. So I feel like from my experience in putting this class together and seeing how it goes from semester to semester, there might be times during the semester where you feel like this. It's important to just try to keep on top of things, to be proactive, to stay on top of the readings, to ask questions, to work with others, and the worst thing that can happen is to fall behind. But if you put time in and you grab the readings and discuss with people, I think things should work well. And with that idea of working together, musicians work together. I'm not a musician, but I like this quote from the guitarist, The Edge from U2, when he gave a commencement address at Berklee College in Boston, which is a music school, and he basically said, you shine brighter if you are working with really great people. So I expect that in this room we have a bunch of people with a diverse set of backgrounds and interests, and through the homework and through the projects, although I ask you to prepare your own homework solutions, I encourage you to work together and discuss ideas with one another, and the hope is that you'll shine brighter if you're working with others. And in a field such as this, which is very interdisciplinary, it's these connections across disciplines, from the medical experts to the materials experts to the chemists to the electronic engineers that make new things and make innovations happen. And I hope we can replicate that sort of model throughout the semester. And then, I don't think our final presentations will be quite like this, but clearly their collaboration results in a lot of celebration when they finish up. And as Bo Schembechler said to the University of Michigan football team about 40 years ago, those who stay will be champions, or I hope that working hard and learning together results in a productive output. And I want to hear your feedback about the class and hear what you're interested in, and I hope to keep an open channel of how we can design dynamically the applications we talk about so we can all get the most possible out of the semester. And I want to encourage you to come to my office hours. You can always stop by if my door is open. Sometimes I might tell you that I'm busy to come back another time, but always feel free to come talk to me, and also talk to me if you have interest in something that might be adjacent to the course and you just want to ask my ideas about it. And I hope to get a sense of your interest too by looking at your information sheets and working on the project. So to close, I just want to play a video. If you've seen The Graduate, you might recognize the scene, and hopefully there's sound.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Nanotechnology.
Exactly. How do you mean?
There is a great future in nanotechnology. Think about it. Will you think about it?
Yes, I will.
Shh. Enough said. That's a deal.
Okay, so check out the readings online. I'll also try to put next time's readings up in advance. And next time we're going to get down to business and start talking about crystal structures and magic numbers. And hope to see you all next Monday.